The flip portion for chapter 7.8 on improper integrals is actually broken up. I decided to go with 3 videos. The first video is this, which is just a brief overview, again, of what an improper integral is. It's basically a definite integral, not in accordance with the usual form that we're used to seeing. There are 2 types of improper integrals. First is the infinite interval of integration, where you actually have an integral that one of the limits of integration, or both, are infinite. And that's going to be what we're concentrating on for this video. And the second type of improper integral is when we have an unbounded integram. For instance, somewhere on the interval of integration, the integrand is undefined. In this case, at x equals 0, we have a vertical asymptote. So we're going to concentrate on the first type in this video. So up to this point, all our definite integrals had finite intervals of integration, and the functions themselves were finite, meaning there were no asymptotes. But the basic understanding, or paradox rather, that we looked at before break was that a curve that goes off infinitely can have a finite area so underneath it. So in this case, we were looking at the curve 1 over x squared, which is actually a special curve that it will be the topic of the second video, and that's the P family. This is a P family curve. And it's a curve of infinite length. It goes on and on and on and on. Yet the area underneath it is finite. In fact, it's 1. And the second video proves the characteristics of the P family curves. So we're going to use limits to help us solve these improper integrals. So the 2 cases that I already laid out for you are here. I'm not going to review them again. The thing that I want you to understand is that we're going to use limits to examine what happens with both of these cases. If the limit exists, then the improper integral converges. If the limit does not exist, then the improper integral diverges. So that's the language that we are going to be using. So to evaluate an improper integral with an infinite interval of integration, we're going to use limits. Here we have these. Right, the limits of integration go to infinity, or both, or negative infinity. So it's infinite in the horizontal direction. So x is infinite, and that's the horizontal direction. So how are we going to go about working with these? Well, we're going to integrate over a finite interval. So we're going to replace the infinite limit of integration with a finite interval, and then we're going to look at the limit as it approaches that infinite point. So let's get specific with some cases, and then we'll do an example. Let me grab another color. So case 1. So case number 1, if f is continuous on the interval, so f is continuous on the interval a comma infinity, then the integral from a to infinity, f of x dx, is equal to the limit, I'm going to come down here, the limit as b approaches infinity, and then we're going to replace that infinite limit of integration with a finite but very large value, b, and we're going to look at this limit as b goes to infinity. If the limit exists, then it converges. The integral converges. So that's the first case. The second case is when we have a lower limit of integration being negative infinity. And that's simply the limit as, I'm going to replace it with a, goes to negative infinity, a to b, f of x dx. And again, the same case here. If the limit exists, then it's going to converge. And the last case and final case is when we have two limits of integration that are infinite. So we're going from negative infinity to infinity. And what we're going to do here is break it up into two individual integrals. So we're going to let a go to negative infinity, a to some point c, where c is just any real number. And then we're going to add to it, we're going to add to it the limit as b goes to infinity from c to b, f of x dx. Okay, so these are the three cases. Both limits have to exist for this to converge. So both limits need to exist for convergence. I apologize for the background noise. My children are running around. And again, c is any real number. Okay, so how do we put this into application? So let's do a problem. Okay, so the application is textbook number 9. We're asked to evaluate the integral or state that it diverges. So one of those two cases are going to exist. Either it's going to converge to a value or it's going to diverge. So let's take a look at the integral. And we see that it's improper because the upper limit of integration is infinity. So I'm going to rewrite this in terms of limits. I'm going to look at the limit as b approaches infinity of the integral from 0 to b, e to the negative 2x dx. And that's an easy integral to solve. Taking the antiderivative, you get negative 1/2 e to the negative 2x, and you're going to evaluate it between 0 and b. And then we'll put back the limit. So let me first go ahead and work out the fundamental theorem of calculus, and then we'll apply the limit. So this is negative 1/2 e to the minus 2b minus 1/2 e to the negative 2 times 0. Okay, so e to the 0 is simply 1. So this goes to 1. And we've got a negative and a negative. So I'm going to rewrite, put the limit back in at this point. So this is the limit as b goes to infinity. And that first term is positive. It's 1/2. So this all resolves to 1/2. And the term with the b in it is what we want to examine. And this is minus 2b. So this is the limit. I'm going to resolve that negative exponent so you can more easily see, and I recommend that you do that. This is 1 over 2e to the 2b. Okay? So as b grows and grows, this term gets large. Very large quickly. And you've got 1 over a very large number. That's going to go to 0. So the answer here is equal to 1/2. So therefore, this integral converges to 1/2. And that's your answer.